Hello, here we are in one more lecture for short tutorial series, in this time differential equations, and we are now considering a very important method to solve differential equations of any order that's called power series method for differential equation solution. So we are using this power, we expressing the solution as a power series to solve a given differential equation. And in the last lecture, I showed to you that what you have to do is take the derivatives of the series, substitute, and you're going to have a polynomial equation that will allow you to get the set of coefficients, and that determines the function. This is what we saw in the last lecture. In this lecture, I'm going to give you some examples. So we're going to start with simple examples, and then we build up a few more examples for you to understand what we are saying about power series method for solving differential equation. So here I start with a differential equation. This is a first order differential equation, it's a homogeneous, the most simple. By looking to it, we know the solution. Can you guess what is the solution? I think so, because if I take this, put this y on this side, right? So this can be expressed as dy over y is equal to dx. And this is the integral of this will give you logarithm, the integral of this gives you x. So we all know the solution will be exponential. But let's see what series, the power series tell us. We have this equation, and we're going to now imagine that the solution is a series. So as I told you, when we imagine that, we consider y as a series of powers of x's, starting ordering 0. And the first derivative, if I take this series, right, this series is equal to, who is this series? Is c0 plus c1x plus c2x squared and so on. That's the series. You agree? When I take the derivative, c0 disappears, and I end by having c1 plus 2c2x plus 3c3x squared and so on. So this is the first derivative. And I could keep going here with all the terms. Minus, there is a minus here, the series itself, which is c0 plus c1x plus c2x squared plus all the other terms, and equal to 0. So this is the first derivative. This is the function. So, okay, this is the function itself. And everything has to be equal to 0. And I have now transformed the simple differential equation. Oh, I know we can solve it by other methods. I did already. But forget about this now. We are seeing that we are able to do by series to show to you the example. So this is now a polynomial equation that originates from the differential equation. And this polynomial equation is equal to 0, which means that all the terms of the same order must be 0. All the coefficients of the same order of x must be 0. So the independent, the term that is x to the 0, which is what? No x, right? Is c1 minus c0. And c1 minus c0 on this side must be 0, because in the other side is 0. So I create the first equation. So here I have the first equation. c1 minus c0 is equal to 0. Now let's see the first order. In this I have 2c2 plus minus, right? Because this minus here is multiplying everything. Don't forget, the minus is multiplying everything, right? I put a big minus there, but this is multiplying everything here. Minus is multiplying everything. So then I have 2c2, and then from this here, I'm going to have a c1. So 2c2 minus c1 is equal to 0. This is another equation that relates c2 and c1. The first one relates C0 and C1. The second relates C2 and C1. Now I'm going to take now the second order term. Here I have 3C3, and in this side I have a minus C2. So 3C3 minus C2 equal to 0 as well. Is another equation. And then I keep going forever with all the terms of the series. And what I'm going to get at the end? At the end, I get this sequence. But I see that C1 can be determined. I need some information from the function, right? And I could give you the information that x equal to 0, the function has a value, which is the initial condition. And I could say that the value is 1. And I know exactly if the function, right, that I'm proposing is this series, when x equals to 0, only the independent term, which is the C0 term, will survive. And if I say that in x equal to 0, y is equal to 1, means that C0 is equal to 1, right? But let's leave as C0. So from the first equation, we get that C1 equal to C0. So here it is. So I express C1 in terms of C0. Now, from the second equation, C2 is equal to C1 divided by 2. But C1 is C0, so C2 is C0 divided by 2. And now, the third equation, 3C3 is equal to C2. But C2 is C0 over 2, which gives me C3. C3 is now C0 divided by 6. So I get the C3. Everything in terms of C0, which will be some constant to be determined given the initial conditions. I could keep going, and then I'm going to have all the coefficients of this series. But you're already realizing that C0 is C0. C1 is C0 divided by 1, which is 1 factorial. C2 is C0 divided by 2, which is C0 divided by 2 factorial. C3 is C0 divided by 6, and 6 is 1 times 2 times 3, which is 3 factorial, and so on. So, I can take this solution now, and just for your control, I could express the solution in an extended form. And I found, by using the power series, that the solution of my equation is equal to a C0 plus the same C0 times x, the same C0 divided by 2 times x squared, the same C0 divided by 2 times 3 times x cubic, and so on. I could keep going, right? And if I keep going, I will find that I can express this series in a very interesting way, which is y of x. I'm going to put C0s in evidence, and putting C0s here, multiplying everything, I have y of x is equal to C0 times 1 plus x squared divided by 2 plus x cubic divided by 6, which is 3 factorial. And I could see that this is true for any other term of the series you go. Of course, I already expressed that way to simplify and for you to identify. But if you remember, who is this guy here? This guy here is nothing more than the exponential function expressed in series. So, y of x is nothing more than the exponential times a constant. And to determine the constant, I need some initial conditions. And any differential equation needs initial condition, right? And here, the initial condition that I am giving is, at x equals to 0, y must be 1. And then I determine that if x equals to 0, y must be 1. So I say that C0, this puts C0 equals to 1. And once I have C0 and I show to you, I have all the terms of the series. And having all the terms of the series allow me to either leave this way, which is nobody can contest you, because this is a truth, or I know that series represents the exponential function, and I express like this. So you see, and as you know, this is what we would get by direct integration of the differential equation, as I did when I start to represent to you. You see, this is a very powerful technique because expressing series, I'm able to obtain the coefficients, I'm able to express the function, I'm able even to go back and put in a closed form this function and know the solution of the differential equation. This is how important is power series for the solution of differential equations. Okay? This was a first order differential equation. Now let's move on, getting a little more. Let's go to a second order differential equation. And I select as a second order differential equation. Another example, still simple, that you may recognize by looking to it. You know, what is the solution of this equation? Everybody knows what's the solution of this equation. You learn from everywhere, especially engineering that we deal with waves. This is basically a wave equation. The solution of this is trigonometrical functions, either sine or cosine of x. So the sum is a solution. I could have an independent term here, but I'm giving it as an example for you to see how powerful it is. So I'm going to keep it that way and solve the equation that way. This is a second order homogeneous differential equation. And again, we're going to propose that the solution is our great series. So I'm saying that y of x is a sum from m equals to 0 to the infinite of Cm x to the m. That's the series I propose as solution. Then, therefore, I have, so this is the function. And I'm going to take the second order derivative to put in this place. So this is what I put here. This is y. And now, as you know, the second derivative, this term disappear, and I'm going to get 2c2 independent, because that will be the first derivative will give me 2c2x. And the second derivative will give me 2c2. So that's the first term of the second derivative. The other term of the derivative will be the terms x cubic. And that will be 3 times 2 times c3 times x. And the other term that originates from the x to the fourth will give 4 times 3. So let's then substitute the series. We have the series on the equation. The function is this term here, c0 plus c1x plus c2x squared plus c3x cubic plus c4x to the 4 and so on. I put extra terms here because so you're going to see what is the first derivative. The first derivative, this term disappears, and I get c1, and then I get 2c2x, and then I get 3c3x squared, and then I get 4c4x to the cubic. And when I take the second derivative, I got, as a first term, the first term of the second derivative will be 2c2, because the first is x. When I take the second derivative, the x goes away. This is the term, independent term of the second derivative. The second term of the second derivative will be 3 times 2 times c3. This third term will be 4 times 3 times c4. And then I will have here 5 times 4 times c5 and so on. So keep going. Okay? So this is the overall substitute equation that now generates the polynomial equation that represents this equation when I put in power series. And of course, I have to consider all the terms. This is equal to 0. So the independent terms must be 0. The sum of the coefficients of the first power of x must be 0. The sum of the coefficients of x squared must be 0, and so on. So when I do this, I get 2c2 plus c0, which is the independent term, must be 0. So that's the first equation. 3 times 2 plus, this is the first order of the second derivative, plus c1 must be 0, because this will be the coefficient. 3 times 2 c3 plus c1 is the term of x in one side. And since the other side is 0, well, this term must be 0. This is the term. 4 times 3 times c4 plus c2, which are now the coefficient, adding together is the coefficient of this x squared, also must be 0. And I keep going. So I get c2 equals to c0 divided by 2. And by convenience, I'm putting as 2 factorial, but because I know what I will get. But this is 2 only. c3 is c1 divided by 3 times 2, which is 3 factorial. You agree? Fine. c4 is c2 divided by 4 times 3. But c2 is c0 divided by 2. So here I get, for c4, I get c0 divided by 4 times 3 times 2 times 1. 1 is there all of the time. And this is 4 factorial. So I put 4 factorial here. And keep it going. I could get all the coefficients, right, for this series. And what's interesting is when I put all together, I get a solution. So the solution is, and then for the, here you're going to see that C0 is going to determine the even terms, and C1 is going to determine the odd terms. When I put all together in the same mechanism that I already showed to you, we find that the function y is epsilon, right? Is equal to, y is equal to C0 plus C1x, and then now all the other coefficients will be expressed in terms of 0 and 1s. And here I put C2, but this is C0 divided by 2, because when I put C2 here, remember we determined that C2 is equal to C0 divided by 2. So that actually is C0 divided by 2 factorial minus, and then there is signs that will appear here depending on the term. So we're gonna get, because in this solution here, when we get C3, there's a minus here, you see? Minus, this is minus. So the odd terms is going to have minus, so they will be negative. And the even terms will be positive. Well, they mix it up, right? So what I have as a series is that I have C0 plus C1x minus C0 divided by 2 x squared minus C1 divided by 3 factorial x cubed plus C0 divided by 4 factorial, and so on. If I put x0 here, multiplying everything, all the even terms can come here, because all the even terms will depend on C0. All the even terms will depend on C0. So C0 multiply this, I get a series here. And C1 multiply all the odd terms, so I put everything in evidence. I mean, what? I'm going to get C1 times x minus x cubed divided by 3 factorial and so on. And then I can identify. I needed to do this identification. No. If I leave this way, it's perfect fine for me. Because normally they're going to give us 2 initial conditions now to solve the equation, which will determine C0 and C1. That's what's going to happen. But because I explained to you that functions can be expressed in series, I'm doing the reverse now. I'm inverting the series with the expression of the function. And this, you can well identify that's the function cosines, and this is the sine. So the overall solution is y equal to C0 cosines of x plus C1 sine of x. Oh, I know that normally people like sine, not sen. But you know, this mixture of language is always interesting. So the solution of the original equation, so we have the equation, and the solution of this equation, I know that you know that the solution of this equation would be a composition of sine and cosine. But we prove by series that it is a solution. Because really to solve this, you're going to have to guess that sines and cosines, which also is valid. When you are able to guess the right solution, you are in the game. But by power series, you don't need to guess anything. The power series is going to show to us what is the solution. And then we get this beautiful solution with all the coefficients identifying sines and cosines. Let me get now a more elaborate equation, because sometimes we're going to have an equation that may be different from that simple one. This is a first order ordinary differential equation, homogeneous, but has functions multiplying the derivatives, right? And we need to solve this. That's a little harder than we have done, right? And we needed to solve. And we're going to solve using what? Power series. And again, we're going to get and say, well, y is a series of x. Good. And that's the series. The series is C0 plus C1x plus C2x squared plus whatever. So this is the function. I already put the series here. And this is it. And now I take the first derivative of this. I get C1 plus 2C2x plus 3C3x squared, the same way we did before, and I put here. Then my equation, my differential equation, transforms now in a polynomial equation, which is x plus 1 times the first derivative minus x plus 2 times the function. And this is equal to 0. Right? And now I first need to do this multiplication before identify the terms of the same order. And here I'm going to just elaborate a little more, and I'm going to keep a generic term on the series. Okay? Okay, so this is C1 times x plus 2C2 times x squared. I'm multiplying x to everything, and then I'm going to add the 1 times everything is here. And you see that this equation here is basically S is the same index. I change it here just to show you a generic term. This is any term of this part, of this first part, this x times this will be S times CS times x to the s. 2 times C2 x squared. 3 times C3 x cubic. 4 times C4 x to the fourth. 1 times C1 x to the 1. So this is a generic term. I kept a generic term here, right? Which is x times the derivative of the series. The second part of the equation, which is 1 times this, this is already, this is the term. So the 1 times this is C1, is the series, right? Is this term here. And this can be expressed as S plus 1 times C, the coefficient, S plus 1 times the power x to the power s. This is a generic term for the second term here. This is algebra, right? You all know how to multiply polynomials and x and times polynomials and constants times polynomial. Now I do the same here. So this is a minus here. We have to take in account. This minus, that is a minus here. We have to take into account. And the x times the series minus C0x minus C1x, see? X times C0, x times C1x, x times C2x, and so on. And this has also a generic term, which is Cs minus 1 times x to the s. And then the final term, which is 2 times this whole term, which is minus 2C0 minus 2C1x minus 2C2x squared, which has also a generic term. It's 2 times the series. And this must be 0. And then you do the same game now. You go and you look to this, right? And everything has to be 0. So all the coefficients of any order of x's in this side, in the first term, has to be equal to 0 because the second term of the equation, the other side of the equal sign, is 0. So everything must be 0 for any value of x. This is what we learn in high school. And we have to apply here. Then, when we do that, the order 0 will be this equation, which is the independent term, right? It's the term that has no x on it. C1 minus 2C0 is the term that comes from the two members. And then the first term will be 2C2 minus C1 minus C0 equal to 0. And I put here when I get to the order x to the s power, I have a generic term. So I put the generic term here. And the first equation allows me to obtain C1. C1 is 2C0. So it's just, I know who is C0. No, that's probably will be given by some conditions. Right? And then I could get, I know C0, I may get C1. I know C1, I may get C2, and so on. So by constructing this collection of equations for all the coefficients, I'm able, remember, this is a first order differential equation. I just need one initial condition to determine. So they will depend only in one variable, one constant, sorry, that knowing I know the solution as a whole. But here I solved the example for you because from this generic term from the power law, which is the one I take from the power s to the power s in this polynomial equation, I took this plus this minus this has to be equal to 0. So this coefficient, this, and this, I add all together. And I created this generic form for the all coefficients. And from that, I can obtain that the coefficient C, S plus 1, C subindex S plus 1 is equal to 1 divided by S plus 1, that comes from this term, times CS plus minus 1, that this term is going the other way, and then the 2 minus S that goes to the other way times CS. So what I have here is a very, very important example because I'm able to construct a recurrence relation for the coefficients. If I know this, I tell you, give me the smallest one, S is 0. If I give you S0, I'm able to determine S2. If I give you here, if I give you S0, I know SC1. If I give you C0, I know C1. knowing C0 and C1, which they are related because they are the independent term. So I know that C1 is equal to 2C0. So if I give you C0, I know C1 because I know C0. Here C0. I know the next term, which is C1, by this relation. If I know both, I know C2. If I know C2, now I know C0, C1, C2. And then I come here and say, okay, now I know C1, C2, I determine C3. And then now I know C3, C1, I determine C4, and so on. And by knowing C1, given by this, I determine C2. And then by knowing C1 and C2, I determine C3. And then by knowing C2 and C3, I determine C4. And I determine everything, so I know all the coefficients. So normally, having the recurrence equation, which is the relation between coefficients of different subindex, I'm able to determine all the coefficients of the series. And once I have all that, I put all together, and here I have the solution. So the solution for that differential equation is this. If I write this, I'm right, I'm correct. But of course, I can put the C0 outside, and then I can identify that everything can be multiplied by 1 plus x, and the final series that I end, it will be the exponential. So I could, if I want, get back the analytical expression for the solution of that equation. Right? Very interesting indeed, right? And this is how important is power law, series, for solving differential equation. So just to resume, you imagine you have a power series solution, express the solution in a power series, substitute in the equation, and find the relation between the coefficients. And this is not hard, because it's much easier dealing with algebraic equation than with differential equation. And once you determine the coefficients, you have the solution. And this is what we call power series method for solving differential equations. Well, I hope you like this lecture of our tutorial, and I hope you return for other lectures in the series. And the next time we're going to be able to do the transformations, using integral transformation to solve the equations. And I think it will be a wonderful lecture, because this is another very powerful method for solving differential equations. See you next lecture. Bye-bye.